Hey guys, welcome to this next exciting installment in dynamics for the second semester. This is just a quick overview of the idea of chapter 12.3, and then in the next video we'll do some other things. 12.3 is rectilinear kinematics, but the focus here is erratic motion. So recall again, what is kinematics? We're just studying the motion of the particle. But in chapter 12.2, we saw continuous motion, right? So what is the difference between continuous and erratic motion? This is 12.2. We looked at continuous motion of the particle. 12.3, this is 12.3. We're looking at the erratic motion of a particle. The difference is really, you can see it in these diagrams here, or these graphs. If I have some kind of motion, say it's even velocity versus time, you can see the continuous motion, which is 12.2, is given by something like this, right? It's a continuous function. There's no sudden changes in the velocity, or if this is the position, any sudden changes in the position or whatever, right? This is continuous motion. Whereas erratic motion, which is 12.3, we do not have a continuous function, but we've got something like a piecewise motion or piecewise function. So over this time period, say 0 to this t1, we've got a certain type of motion. Say this is our position time curve. We've got a certain type of motion. Then at that time, it changes to another type of motion, right, up till another time, and then it changes to, again, right, this is just an example. So please pick up the idea, the difference between continuous and erratic motion. The next thing which I want to just discuss quickly is the basic idea in this section is we're going to draw graphs. In 12.2, the continuous motion, we never really saw any graphs because we had one function. We had one continuous function, which was, so in 12.2, you could have had something like this, 3t squared minus 6t, okay? I mean, you definitely could have drawn graphs for this, but perhaps what the writers of this textbook was saying is that it's easier for us to solve erratic motion when we are drawing the graphs, okay? So we need to understand how the graphs are related to each other. For example, if we've got, this is just conceptual, okay? If we've got a position time curve, how do we construct the velocity time curve from the position time curve? Well, we know, and I'm not going to go through all of this because I'd rather do an example. This is just a basic idea. If we want the velocity from the position, right, and it's a position time curve, and we want velocity time curve, we need to take the slope, right, of the position time curve. So we look at the slope at each of these positions, and if the slope is positive, we have a positive velocity. The slope is still positive, but in this case it's slightly less positive. There we have a slightly lower velocity, etc., etc. And what do you notice here at the top? The slope of ds dt is 0, so we're going to get a 0 velocity there. So the point is, I'm not going to go into all this theory at the moment. The point is that we try to use graphs and information from the graphs to break up the problem, right? Okay, so how do we solve these problems? Again, here is an example, but I'm not going to do the example. I'm going to do another problem. The basic idea is this zooming in? Is that okay? Okay, so the basic idea is we need to, first of all, so this question gives us a position time curve. Excellent. And it asks us to draw the velocity time and acceleration time curve. So the basic idea, an overview of how to solve these problems is, first of all, you need to identify how are you going to move from position time to velocity time? That's the first thing. And what did we do in 12.2? We just looked at our variables. On the one hand, we should know that position time, if you differentiate this curve, you're going to get velocity time, okay? But if you're not there yet, what are the variables that relate position and time and velocity? Position, time, velocity. Those are the three variables in this problem. Well, what relates those three is this, v equals ds dt. And we know that velocity is the derivative of the position time curve. Okay, so that's the first thing we need to do, is identify what we're looking for and how we are going to get there from what we have. Okay, then the second thing we need to do is we need to break up our problem into its different time periods. Okay, so for example here, between 0 and 10 we have a certain function, and from 10 to 30 we have another function. Okay, this is a piecewise function. It's erratic motion. So over between 0 to 10 we break it up and we just isolate the function there and we solve. From 10 to 30 we isolate that function. So 10 to 30 we isolate that function and we solve, and then we draw the graph of our vt, right? There's our velocity time based on what we found here. Okay, and then again we do exactly the same for our acceleration time. We break it up. First of all, we have to identify the correct fundamental equation, and in this case it's a equals dv dt. Okay, so we have our velocity time graphs or curves over the two time periods. Now we just say, well, our acceleration is the derivative of our velocity equation. Okay, so again we break it up into its different time periods. 0 to 10, what is my velocity? And my acceleration is dv dt. 10 to 30, what is my velocity? Acceleration is dv dt equals 0. And we take those two and then we construct our acceleration time curve. So what you'll notice here is that we are moving from position time to velocity time to acceleration time. Okay? Which means we're just taking the derivative of the position time curve. We get the velocity. We're taking the derivative of the velocity time curve to get the acceleration. In this next problem, 12.7, in a sense we're working backwards. We have acceleration time, but we're trying to find velocity time, okay? And from velocity time, we're trying to find position time, okay? So again, the point is you need to look at what you have, all right? A is a function of time. What am I looking for? Well, in this problem, I'm looking for velocity time and position time. So now, instead of differentiating, I need to integrate my acceleration to get to velocity. I need to integrate my velocity to get to position. Okay, and again, we break it up into its different time periods, 0 to 10. What is my acceleration? But now I need to integrate my acceleration equation to get my velocity equation. I break it up into 10, I break it up into the second period. What is my function? My function is, acceleration is minus 2. I need to integrate that. I get a velocity equation over that second time period. Then we need to do that again for position. Okay, but now I've got this graph, this erratic motion graph between these two time periods. I need to do exactly the same thing to obtain this graph. Okay, so that is really just an overview. I hope it helps. See you in the next one.